So today we are going to discuss a few different results: Dyson series, Wick's theorem, and Propagator. So in essence, what we're going to do is we're going to finish our calculation. So our goal for this course is to understand how to calculate the scattering amplitudes. This is a scattering amplitude. It's also known as a matrix element. Another terminology you'll sometimes hear me use. So the reason it's called a matrix element is you can think about S, which is the time evolution operator from minus infinity to plus infinity, as some giant matrix. And it has matrix elements which tell us about the scattering amplitude from some initial state to some final state. And if we can compute all those matrix elements, we've essentially solved the theory. We know how to evolve any initial state to any final state. So computing those matrix elements is another way to think about our goal for this course, of this matrix element S. So last time we saw that we can relate this matrix element by the LSZ reduction formula to correlation functions. These are vacuum expectation value of some time-ordered product of fields, and we were working in the Heisenberg picture. What we're going to do today is understand how to compute these correlation functions. And we're going to do that by going to the interaction picture and using perturbation theory. So in general, these correlation functions can't be computed exactly, but there's a systematic procedure for computing them at any order in a small expansion parameter, which we'll discuss. So that's what we're essentially going to use Dyson series, which you discussed with Bindia, to relate this Heisenberg picture expression to an interaction picture expression. And finally, we'll be able to compute interaction picture correlation functions by using Wick's theorem, which relates a correlation function with m fields to a correlation function with 2 fields. And this object here is also known as the propagator, for reasons we'll discuss at the end of class. It's related to some of the things David has been telling you. Okay, so that's where we're going. We did this part yesterday, and we'll do this the remainder today. So last time we did not need to specify a Lagrangian or Hamiltonian. We are going to do that today. Today, that's basically going to be our starting point. We're going to assume that our Hamiltonian can be broken into 2 parts. Part which I'll call H0, which is a free part. And for the purposes of this course, our free Hamiltonian is always going to be the Klein-Gordon Hamiltonian, or the complex version of that, or the sum of several copies of it. So some version of the Klein-Gordon theory here. And we'll assume that there's some other interaction, extra interaction term. H1. I won't specify what that that is at this point, but we'll assume it's in some sense small. Okay, so our basic thing we need to do to relate Heisenberg picture expression to the interaction picture expression is rewrite both the fields, Heisenberg picture fields, in terms of the interaction picture fields, which is straightforward to do. But we also need to relate the interacting vacuum to the free vacuum here. So those are the two things we need to do. And the first part you've already essentially seen in Bindia's part of the course. So we have the Heisenberg picture fields. You can write them as interaction picture fields. I'll denote by phi naught. And this just evolves with the free Hamiltonian, I h e minus t naught minus I h e minus t naught. And here I've done something perhaps slightly different. So I'm assuming here that t naught is the reference time at which the Heisenberg picture and Schrodinger picture and interaction pictures all agree. Often we'll take t naught to be 0, but we don't have to. So this is t naught is typically 0, and for some purposes that's fine, but other times it's useful to keep this explicit. Sorry, this should be t naught here. I can write this in another way. Also write this as some time evolution operators. U of t, t naught, phi naught, x, t naught, of t naught, t. I can also write this as U of t, not dagger.
By Heisenberg operator, you mean it has been evolved using H naught?
H naught. That's essential. Thank you for catching that. Absolutely, yes.
Doesn't the interaction picture operator also have time evolution, or is it just stuck at t naught?
Yes, it also evolves in time.
Was it a specific reason why you wrote U as that goes from t to t naught instead of going from t naught to t? So it would be U dagger phi U. Because normally it's defined that way.
It's the same thing.
The same thing. So this is.
Just wondering why you wrote from instead of t naught comma t comma t naught, so that it would be U phi U dagger as opposed to U dagger phi U. Is there a particular reason?
No, you can write it either way, so it's fine. So this is the same thing. Okay, and so you studied this time evolution operator U with Bindia, and so this can be written in several ways. U of t T naught can be written as product of, sorry, this should be a T. U can be written as the exponential of H naught T minus T naught e to the minus I H T minus T naught. Or it can be written in the most useful form for us as a time-ordered exponential. So I think this is a slightly different notation than Bindia used. Time-ordered exponential of minus I integral from T naught to T of H prime. Is this expression familiar, or should I explain a bit more? Mary?
T naught, should it be H minus H1? If U is an operator, is it an operator for the full one, or just the perturbation, or?
The interaction picture fields evolve with the free Hamiltonian. That's what makes them so useful. Is we explicitly know how to do evolution with the free Hamiltonian.
Yeah, so it is the free Hamiltonian. So should then U of T be e to the I H1 minus IH?
Let's see.
I think the question is, are they the same U or different U's?
These are the same U's. This should be the interaction part. Interaction Hamiltonian. That should not have been the full Hamiltonian.
Maybe the confusion is like the interaction picture will evolve with H naught, but we're writing the one for the Heisenberg picture.
Mm-hmm.
So even though the interaction picture evolves with H naught,
I have this back. I'm very sorry. Sorry, my apologies. This should be H over here. This should be the interaction picture. My apologies. This is Heisenberg. There we go. So the interaction picture fields evolve with the free Hamiltonian. The Heisenberg picture evolves with the total Hamiltonian. Schrodinger picture operators don't evolve.
Well, sorry, what I'm saying is like the way you've written U of T and T naught here is like e to the I H naught minus IH, right? Which is just going to be H1. So is it H1 in the exponent or is it H naught in the exponent?
Here?
No, the line above.
Line above, this is H naught.
No, the one that you wrote
The
apparently as
expression for U
there are
of T.
two expressions there, but I think what you meant is you could define. So the second term is also H naught, I think, and you were just saying that you could define U as the first expression or the second.
Yeah. Yes. This should be okay. This should be a. We can write it in either of these ways.
Heisenberg evolves with a full H, and
Yes.
the interaction picture evolves with only H naught.
That's right. Yep.
And then it should be H1 in the exponentials to sort of balance.
I think it was correct before, like.
So this okay. Correct before with the T here.
The first line is correct.
Like that. Yeah. Yes.
Why not T naught at the beginning?
T naught, yes. Yeah, T naught here and T here. T naught here.
I think the confusion is with the subscripts of H, not of T.
I guess, sorry, the confusion for me is, like, okay, going from the very top of the board, like the first line, where the H naught is in the exponent, like if that's equivalent to the second line, like U of T naught, right, that means that U of T naught is e to the I H naught T minus T naught, right? But then in the third line, you're basically saying U of T naught is e to the minus IH1. Like if you combine those terms. So is it IH naught or is it IH1? Is my confusion.
This is IH naught.
Yeah, so
Okay.
You could probably just explain what the third line.
Third line.
yeah, should that be IH1 minus IH instead?
So we can write.
I think the U's are not the same as
Uses not the same.
the second U is not the same as the first. The fifth line is not the same as the first line. Is that psi on that phi or psi on the second line is in terms of T instead of T naught?
T naught. Okay. I'm confusing myself here. So the if we can write the interaction picture operator at some arbitrary time by taking the Heisenberg picture operator at the reference time and evolving with the free Hamiltonian. That should be okay. And also write it.
I think here we evolve with time t, but it's in the Heisenberg picture, so we use the full Hamiltonian.
Yep.
So it's t, not t naught.
T naught here. Second line. That's right.
And the operator explains both evolutions together.
Yes. Thank you. Yes. So that we can write this here is a t. This is a t naught. So if we write this in terms of the time evolution operator, we get an extra factor of e to the IH t e to the minus IH t. That's where this comes from. Thank you.
We bring any operator to the reference point, and then we evolve further with A0.
That's right. Yes. Okay.
So did you assume that H is commute there?
No, I don't. So that's a key point. So that's why I can't combine these exponentials. This is in general not equal to exponential of H naught minus H. Okay. So this is how the operators evolve after my apologies for those mistakes. The other thing we need to determine is how to relate the interacting vacuum to the vacuum in the interaction picture, or the free vacuum.
Sorry,
Gotcha.
going back to this. Can you just clarify really quick? So does the Heisenberg picture that evolved with? Is it the full Hamiltonian or the free Hamiltonian?
The Heisenberg picture evolves with the full Hamiltonian.
Okay, so that's the full Hamiltonian. So then the interaction picture, interaction operators evolve with the free Hamiltonians?
The interaction picture, yes, they evolve with the free Hamiltonian.
Okay.
Okay. Okay, so the next thing we need to do is relate the vacuum of our two theories. And what we know is that we take the annihilation operator. I'll work here in the Schrodinger picture. Annihilation operator at the reference time, T naught, and apply it to the vacuum of the full theory, the interacting vacuum. At any time, we get 0. This was basically an assumption of that we made in the LSE reduction formula, that we assumed that our annihilation operators at any time, any fixed time, work the same as they do in the free theory. And we can write this, and so this works for any time. So in particular, it works for t equals plus or minus infinity. We can also write this as AP t naught e to the I h t minus t naught times omega of t naught. And this is 0. So that's what we know. That's basically what we assumed in the LC reduction formula. We also know that in the free theory, we take an annihilation operator. Again, I'll work in the Schrodinger picture, and act with it on the vacuum of the free theory at any time. I get 0. And in particular, this is true for t equals plus or minus infinity. And that we can write this with the explicit time evolution of the vacuum state as AP of t naught AP of t naught e to the I h t minus t naught of 0 at t naught. And this omega of t naught and 0 of t naught are our Heisenberg picture states. They're at our reference time. So and there's no time evolution of the states in the Heisenberg picture. And what we see, we compare these two equations, is that we have our annihilation operators, the same in both of these equations, acting on some state gives us 0. If we assume that the vacuum is unique, then we must have that these two states are the same up to possibly some normalization. We must have that omega, the Heisenberg picture state, or omega of t naught, so the same thing, should be equal to some normalization constant, the limit t goes to minus infinity of this times e to the minus I ht. This should be the free Hamiltonian. And this is just the time evolution operator, U, from evaluated, evolving from time t naught to time, from time minus infinity to time t naught.
Sorry.
Sorry then, are we evolving the vacuum states like omega and 0 in the Schrodinger picture? So should the exponents have a minus in front of the Hamiltonians?
minus. Yes, there should be minus signs here. Thank you. Did I get these signs wrong? This is. That's okay. This is okay.
What we've written here, we assume that it should be plus, else this would be like for the operators.
Which operators?
What we have here, the interaction picture, that relation, that would work only if states evolve with e to the power ih and not minus ih. On the left side of the board.
Left side of the board?
This relation is true, but it will work only if the like state operator, like the wave states evolve as e to the power ist and not minus ist.
Did I make a sign mistake?
If you flip the limit of the left hand side.
Here?
No, like when you're writing the time evolution there, because that's the u, not
Oh, okay. This is u, should be from t naught to t. T to t naught, yes. T to t naught.
When you say if the vacuum state is unique, you're saying that the vacuum state at t equals 0 of the interacting theory is the same as the vacuum state at t equals 0 of the free theory.
That's what we're assuming, yes.
But I thought the ground states were connected to the Lagrangian of the theory itself, so wouldn't it be specific to the particular theory that we're talking about?
So the normalization can change. That will change in general, even if we do a small change in the Hamiltonian. But what we assumed is that the annihilation operators work in the same way. So they should annihilate the vacuum state for all time in the interacting theory with that assumption, and the assumption that there is some time at which the free theory and the interacting theory agree, that we can go to the interaction picture. These two equations, together with the assumption that the vacuum is unique, imply that there can't be a significant change. That these two states are the same up to a normalization. Sure.
Sorry, what's that next to the n? Is that like an I or is it a subscript?
It's a subscript I. So this is the initial state normalization. So here I have a limit t goes to minus infinity. This is n sub I.
Okay.
We can also write down an equation in the limit t goes to plus infinity. There'll again be some normalization constant, and I doesn't have to be equal to nf, the normalization as we go to plus infinity. So we also have we can also write down the same equation, almost the same equation, limit as t goes to plus infinity, nf u infinity 0 is shorthand notation for infinity comma 0 acting on 0. So we can do this in either limit. The normalization constants might be different. Yes.
Sorry, these vacuum states, ket omega and ket 0, are these at a particular time, t naught, or?
Depending on which picture I'm looking at. So the first equation I wrote for each was in the Schrodinger picture, where they're time dependent. Then I wrote them at a fixed time, which could be the Heisenberg picture state, or at the reference time. And so there's some normalization constant here, and Ni in general is not equal to NF. Okay. So now we have basically all the ingredients we need to relate the Heisenberg picture correlation functions to the interaction picture correlation functions. So let's plug in our results. So we're interested in computing this Heisenberg picture expression in the interaction picture. And let's assume, for simplicity, that this is already time ordered. So x1 naught is greater than or equal to x2 naught, and so on. The general expression will be very similar, and we can figure that out afterwards. Okay, so if that's the case, you can just drop the time ordering. And what we get, and use our results. So for the raw vacuum, I can write I'm going to use this equation, write it in terms of NF, and 0, and then with the time evolution operator from 0 to infinity. For the ket vacuum, I'll use the other relation, and write it as 0, u 0 minus infinity, and then get the normalization constant ni. And then I can write also the Heisenberg picture field operators in terms of the interaction picture time evolution operator. So phi of x1 is u 1, 0 times phi naught of x1. Then on the other side, I have a u 0, 1. Did I get the? Should be the other way around. I have the sign wrong. U 0, 1, u 1, 0. And so on for all the other operators. And then I'll have phi naught xn up to and then u of n 0. So these operators can be combined. I've got here a product of a time evolution operator from time 1 to the reference time, and then from the reference time to infinity, evolving in time to the reference time, and then continuing to time evolve is the same as evolving just from time 1 to infinity. So I can combine these two time evolution operators using the composition property and write this as nf ni 0 u infinity 1 phi naught x1. I'll have u 1, 2, and so on up to phi naught of xn, un minus infinity. So I've used the composition property here. Now at this point, I can note that all of the operators here are in time order. So the latest time is on the left, this time evolution operator. involves operators between time 1 and infinity, then an operator at time 1, and between time 1 and 2. So this is time ordered. I can insert a time ordering here. Okay, and once I put the time ordering, I'm free to move the operators around however I like. So in particular, I can push all of the time evolution operators together and use the composition property again. And I just have a single time evolution operator from minus infinity to infinity. Okay, so we're almost there. Last thing we need to do is just determine what these normalization constants are. And we can determine those by looking at the ground state. And comparing two expressions for the norm of the ground state. So by assumption, we'll assume that our ground state of our interacting theory is unit normalized. We can also write this equation in using this equation and the corresponding equation for the initial time. Write this, the raw vacuum as 0, u infinity 0, and the times n f, and the ket vacuum as ni u 0 minus infinity. So that tells us that ni and f is 1 over u infinity minus infinity. Yes?
Shouldn't that be u infinity 0 dagger?
So I've used the fact here that u dagger. Here we're using that u dagger of P1, P2 is u of P2, P1. Taking the dagger is basically doing the opposite time evolution.
I was confused because if we take the transpose of that equation.
It should be u0.
This, should that be u0 infinity? Yes, thank you. It should be u0 infinity. And to be consistent, I think it needs to be NF star, or how I used it everywhere else. Okay, so we essentially have our putting these results together, we get our final results. So the Heisenberg picture correlation function is equal to a ratio of interaction picture correlation functions. just leave it in terms of the time evolution operators for now. Okay, we're almost there. Also be useful to rewrite things instead of in terms of the Hamiltonian, in terms of the Lagrangian. And for the cases of interest to us, the interaction Lagrangian will be, or the interaction Hamiltonian will equal to minus the integral of the interaction Lagrangian. We're going to be interested in interaction terms that are just polynomials in the fields. So they won't depend on the time derivatives of the field, and that it's the interaction Lagrangian will just be related to the interaction Hamiltonian by a minus sign and an integral. So with that, we get our final expression for the correlation function, just in the interaction picture. And this is a key formula that we'll be using over and over in this course and future courses in order to compute these correlation functions that are objects of interest. And so far, we've made no approximations. To go further, what we're going to have to do is Taylor expand the exponentials. So we're going to write the time-ordered exponential as a series. And by truncating this term, we'll get an approximation correlation functions we're interested in. We're going to consider the case where interaction Lagrangian is a polynomial in the fields. Then what we need to compute any term in this expansion is just correlation functions or free fields. Each term will be something of this form, also with some extra numerical factors and integrals. So these are what we need to compute. And one note of warning. The series expansion in general does not converge. Instead, it's asymptotic. An asymptotic series is one that if we take a fixed number of terms, and the approximation gets better and better as we make our expansion parameters smaller and smaller. It's not true that this series always converges. There are many well-known examples that we'll study in some detail where the series diverges. It doesn't mean it's not useful. Truncating this series to a finite number of terms often provides an excellent approximation to the original quantity of interest. And in fact, some of the most accurate predictions in the history of science in quantum electrodynamics are developed by using asymptotic series expansions that don't converge and just truncating it. And you can test that to 9 or 10 digits, which is extremely impressive. So, in some of the elective courses, we'll discuss reasons for why this doesn't converge and what that means and what that tells us about the physics of this system. But just something to keep in mind for now.
Sorry, the time-ordered exponential in the final expression, should there be a minus in front of the I? Because the interaction Hamiltonian is a negative integral of Lagrangian density, and then the u of infinity to minus infinity is going to be like a plus I integral from minus infinity to infinity.
The u has minus I.
Yeah, it's a minus I, but from infinity to minus infinity. So when you flip it around, you just get a plus I.
Okay. This final result, I'm confident of the sign. I probably made a sign mistake somewhere else. Again, my apologies for that. In the notes, it should be correct. I should have looked more carefully at my notes for the signs.
Like the series necessarily does not converge, or there are some cases when it does not converge?
Typically, it does not converge. That's the general case. I think you can construct examples where it converges, but those are harder to do, harder to find. I don't know of a general argument that it can't converge, but in fact, proving it doesn't converge is hard. But there are some physical arguments that apply in many cases, but not necessarily in every case where you can argue that it doesn't. We'll discuss those more in some of the elective courses.
I think that maybe it's a similar question. Could you repeat the notion of asymptotic series?
Okay, so an asymptotic series. First, let me remind you what a convergent series is. A convergent series is one where if you take more terms with a fixed value of your expansion parameter is some small parameter a. If you fix a, take more and more terms, your approximation will get better and it will approach the true value. That's convergent. Asymptotic is different. You take a fixed number of terms, and as you vary the expansion parameter a, if you take a to go to 0, then that will become a better and better approximation with a fixed number of terms. So a series can be both convergent and asymptotic, but it can also be asymptotic but not convergent, and that's very, very common.
That parameter is dimensionless?
Yes.
And it's related to the energy scale of, it's like a comparison with, or what's the physical meaning of that parameter here?
You can. There are many different expansion parameters you can do, and this is general. And for most quantum field theories and most parameters, it will be asymptotic and not convergent.
So if we take, say, a fixed number of terms, like what would be the difference if we took fewer terms or more terms, and in both cases, made the expansion parameter go to 0? Like, we would get different results, wouldn't we? Like, based on how many terms we have.
Yes. So for an asymptotic series, I can draw a sketch of what typically happens. Oh, this is a sketch of the error versus the number of terms. What's tip with a fixed expansion parameter. It's typically the case that take a very small number of terms. Error can be large. It will increase as you take. The error will decrease as you take more terms. but generally there's some minimum error. So taking more terms in your series beyond that with a fixed expansion parameter doesn't help, and this will diverge. This is typical. It's not, you can come up with examples that don't have this behavior, but this is very typical. Yes.
What do we mean by error there? Like how do you?
The error, I mean, the sum of the first n terms n is 0 to I is 0 to n minus the true value divided by the true value, something like this. So if we're saying we have an asymptotic series, f of x is asymptotic to some series as a goes to 0. Some coefficients times a to the n. This would be, the true value would be f, whatever we're trying to approximate. Some of the first terms will be, truncate this, only consider 3 terms.
So in practice, you would take the number of terms that gives you the minimum error, and then you decrease the expansion parameter.
In principle, that's what you would want to do to get the best possible approximation. In QFT, generally the effort required to get one more term grows very fast. So usually we can't reach this point in QFT. In other areas of physics, asymptotic series are also useful, and in some cases you can, particularly in some numerical problems, you can reach this.
So how, I didn't quite understand how you calculate the error. How did you calculate the error? Because, no, because you don't have the true value. So.
Yes, in QFT, often we don't know this exactly. Still, there are, if you know something about this, you can often estimate this, how many terms is the optimal.
How exactly?
Let's discuss after class. That's rather big. Yeah, this is an interesting topic. It's we'll come back to some of this later, but this is getting a rather big detour from where I was trying to go. So happy to discuss with anyone after class. Okay. So that is here. This is a good spot to take a break. Let's break for 5 minutes. Our next goal is to compute the correlation functions in the interaction picture. In the interaction picture, operators evolved just with the free Hamiltonian, so they behave just like the free field operators. And we've written the correlation functions in terms of the free vacuum too. So I'll often refer to the interaction picture as just the free theory. So they essentially behave in the same way. We compute things in the interaction picture in the same way we would in the free theory. So essentially what we need to do is understand how to compute these correlation functions in the free theory. And we basically have one tool at our disposal, which is the commutation relations. We can expand these operators in terms of the creation and annihilation operators, use commutators, and compute these functions. So we could do that on a case-by-case basis, but since we're going to be computing these things frequently, it's useful to get a general formula for how what the result of using the commutation relations lots of times will be. That's essentially what Wick's theorem is. So Wick's theorem relates time-ordered products to normal-ordered products. And to remind you, normal ordering means moving all of the creation operators to left and annihilation operators to the right. This means having the latest to the left. And the result, I'll present the result in a minute, but let's first break up our field into two parts. A part containing the creation operators, we'll call phi sub plus, a part containing the annihilation operators. Phi plus is just half of our expression for the free field. There. And phi minus is the conjugate. Okay. So I'll present the general result in a minute, but before, let's just look at the simplest correlation function, or simplest non-trivial correlation function, which is the two-point function. So if we want to compute this, let's not do the vacuum expedition value yet. We just want to relate this time-ordered product to a normal ordered product. We can expand out phi of x and phi of y in terms of phi plus of x and phi minus of x, and similarly for y. We do that, we'll get four terms. Let's assume for now that x naught is greater than y naught. We get four terms. So if x naught is greater than y naught, this is already time ordered. We get four terms: phi plus of x, phi plus y, phi plus of x, phi minus of y, phi minus of x, phi plus of y, and phi minus of x, phi minus of y. And all but one of these terms is already normal ordered. Which one is not?
What did you say?
Which one of these terms is not normal ordered?
The second to last one.
This one.
That one.
Yes. So this one has annihilation operators on the left, which means it's not normal ordered. So this term we can rewrite as phi plus of y, phi minus y plus the commutator. And so this is for the case x naught is greater than y naught. If y naught is greater than x naught, then we're essentially interchanging x and y. So in general, if we combine the two cases, we can get time-ordered product is equal to the normal ordered product plus, well, we have commutators. We have two commutators. And if x naught is greater than y naught, we have the commutator phi minus of x, phi plus y. And in the other case, we have phi minus of y, phi plus of x. And this combination of commutators and Heaviside step functions shows up over and over again. So it's useful to give this a name. So we'll call this part here, orange box, is defined to be contraction two fields. This has many names, but for now we'll call it the contraction. And this contraction is a complex number. There's no operators left. You do the commutator phi minus with phi plus. We know the commutator of that'll be proportional to the commutator of a minus with, or ak with ak dagger. And that commutator is just 2 pi cubed 2 ek and delta. There's no operators left. So these are numbers. So this is normal ordered. If I had a normal ordering on this, on each of these terms, I haven't changed anything. There's no operators. It's normal ordered. So, given this simple example, I can now state the general result of Wick's theorem. Theorem. So Wick's theorem says, in general, time-ordered product n fields. So by here phi sub I mean phi of xi. Is equal to the sum of the normal ordering of all possible contractions.
Sorry,
Okay.
I think this is a slight mistake. It should be yx. Right there, it's phi plus y, phi minus y. Is that right?
This?
For the one,
Yeah, phi plus
Yeah,
x,
phi
phi
plus
minus
y.
1.
Y plus x phi.
but to the left of it, the term to the left. Yeah,
They're
yeah.
both y.
Oh, they're both y's. Oh, thank you. Yeah, this should be phi minus x. So that for the case of two fields, we've already seen this is true. There's one way to not contract the fields and one way to contract the fields. Let me give you another example. If we have three fields, this is equal to the normal ordered product of those three fields. And we can also contract the first and second field. Leave the third field uncontracted. You contract the first and the third field, or we can contract the second and the third field. So note that in this case, there's no terms where all the fields are contracted. And the reason this is useful, the reason Wick's theorem is useful, it's a statement about operators. The reason it's useful is that when we're computing vacuum expectation values of these products of operators, the vacuum expectation value of some normal ordered operators is 0. If there are any uncontracted fields, then the vacuum expectation value is 0. So I take the vacuum expectation value of time-ordered product of three fields, it's 0. Two fields, it's equal to the contraction. And for this reason, this contraction is also known as the propagator. This is the propagator. Yes, Mary?
Sorry, I think I'm just a bit confused about the notation. So the contraction, like the term phi x phi y with like the arrows between x and y, is everything in that box.
Everything in the box. The step function times the commutator plus the other step function times the other commutator.
And that evaluates to a complex number.
Complex number, that's right.
And this is a general result, not assuming that x naught is greater than y naught?
No, so we get, if x naught is greater than y naught, this term is 0. That's what we showed up here. If y naught is greater than x naught, that means we're starting with phi of y on the left. Everything over here is the same, except we just switch x and y. And that's what this term is, this term with x and y switched.
And what's
Yes.
the physical meaning of the propagator? We say propagator as green function.
That's right.
And the other question, what's the meaning of it being complex instead of green?
Well, so one way to think about this is phi of y acting on 0. This is a one particle state. In a crude sense, this is a one particle state localized at y. It's dangerous to take that too seriously, but it's useful for getting some intuition. So this is it's certainly true. It's a one particle state. And in a sense, it's localized at y. This does not mean that there is a position operator that acts on the state as an eigenvalue y. That's not true.
Why? What sense is it localized at 1y?
So in a sense, this is like the Fourier transform of the momentum state. So in non-relativistic quantum mechanics, we have kx e to the ikx. In QFT, we do have k phi of x 0 is e to the ikx. So in that sense, this is analogous. In non-relativistic quantum mechanics, we also have that x is that. We don't have that. There's no analog of that, no precise analog of that. So in a sense, it's a one particle state localized at y. There's some ways in which it's similar to the state x from quantum mechanics. And we're essentially taking an inner product of the state with another one particle state localized at one localized at y, one localized at x. So it's telling us something about the amplitude for a particle to go from y to x.
And this is, in general, real because the two will commute?
Phi of x and phi of y commute at equal times. At unequal times, they don't.
So it could be complex.
It could be complex. So in the notes, I give a sketch of Wick's theorem. Happy to discuss that if anyone has questions. But the basic idea is the same as what we did here. You can, in fact, use induction and just assume it works for n. N fields, add an extra field, and repeatedly commute the last field. I do want to say a few more words about the propagator before the end of class today. So the propagator, we can think about as the amplitude for a particle to go from y to x, and it's, in a sense, a building block that we can use to get everything else. Wick's theorem relates a general correlation function to the two-point correlation function, or the propagator. And so the propagator is what we'll use to build up everything else. You've already computed this correlation function without the time ordering in one of the in the first tutorial. And what you saw was that y of x, y of y, with no time ordering, it's just an integral with a e to the plus minus I p dot x minus y. This is, you showed this in the first tutorial near the end of the first question. So we can use this result to build up the time-ordered correlation function, which is the interesting one for us. This is what we need to compute the endpoint correlation function with time ordering, which is what we need to compute the scattering amplitudes, or first the Heisenberg picture correlation functions. And so the time-ordered propagator has two terms. I'll write this as integral d3k so if x is greater than y, x naught is greater than y naught, then we get the result we had before. And this is implicitly evaluated at a naught equals ek. We also have another term. And I'm going to write the other term in a strange way. I'm going to write it as e to the minus I k at x minus y. So it should be y minus x. The other term has x and y swapped. I'm going to write it as x minus y. And I'm going to have this be evaluated at a naught equals minus ek. That fixes the sign of the 0, 0 component. And the sign of the spatial components, we can do the same thing we did a few lectures ago when we switched the change of variables k to minus k. Given this result, I can write it in another way that's going to look rather strange. It's not going to be obvious how to go from this line to the next, but we'll try to understand how to go backwards. I'm going to write this as an integral d4k. I'll write it d3k, and then an integral k0 to 2 pi along a contour that I'll specify in a second of I over p squared minus m squared e to the minus ik dot x minus y. Okay, so this contour, this is a contour integral. Okay. K squared. And k squared minus m squared, we can write as k naught squared minus k squared minus m squared. Or k squared minus k naught squared minus ek squared. So thinking about this as a complex integral in the k naught plane, there are two poles. There's a pole at k naught equals ek, and a pole at k naught equals minus ek. And this contour CF, F here stands for Feynman. It's going to be a contour that goes below the pole at minus ek and above the pole at ek, just with some infinitesimal detour around the pole. Okay, so, and to see that this expression is equal to the expression above, we can try to complete the contour and use the residue theorem. Relate this line to the line above. To do that, it's most useful to choose a contour where the part we add goes to 0. And if x naught is less than y naught, this upper half circular contour vanishes. And if x naught is greater than y naught, then we can do the same thing for the lower half circle. So if x naught is greater than y naught, this bottom half vanishes, and we can use Cauchy's residue theorem to commute the integral along this closed contour. It's just equal to the contribution from this pole.
Why would it vanish without that condition? Because
well, that's
k squared in the denominator, so.
But the exponential wins in the limit that the magnitude of k goes to infinity. So we care about the coefficient of the magnitude of k. So there's a minus I here. So if we have another minus I, then this will be a decaying exponential. That will be the case if x naught is greater than y naught, if we're on this semicircle. If we can look at this point where k naught is imaginary and has a negative, purely imaginary, has a negative imaginary part, then we have two minus i's, so a minus 1 times something positive, so that will decay down here, and likewise on the top. So if x naught is greater than y naught, we just get the contribution from this pole at ek, and that's if x naught is greater than y naught, is this step function, and the residue will give us this 1 over 2 ek. Similarly over here. So this is a very useful way to write the propagator, and sometimes we write it instead as I over k squared minus m squared plus I epsilon. Instead, this I epsilon you can think of just as a mnemonic about which way to go around the poles. So implicitly going to 0.
Like we were discussing this yesterday in classical as well. So what if instead of taking like a detour around the pole, we define the integral to be the principal value? Will that somehow affect our final result?
The principal value. We can relate this propagator to the principal value plus a delta. There's relations. You can think about this as a distribution. The I epsilon prescription as a distribution. So it's a sort of generalized function, and that's equal to principal value plus or minus a delta. I don't remember what it goes.
Like this 1 by k square minus m square is similar to the Green's function in Fourier transform.
It is a Green's. Yeah, this is a Green's function. Yes.
But like we were getting that Green's function is Green's retarded plus Green's advanced. If we take a particular if we take the principal value, we get gr plus ga. But I think if we take this loop, we get only gr, something like that.
This is
contour. So if you go from the lower part of the quadrants or from the upper part, you would get different results in the E&M course. That's what he's talking about.
Or the integral along the integral is defined to be along this contour, which is not closed. We can make a choice of contours to compute this more easily. There's nothing stopping us from closing the contour down here if y naught is greater than x naught. It just won't be useful.
What is that if you change the configuration of the way that you draw the half circles around the poles, would that make any changes in the
Yes. So this is the Feynman propagator.
Yeah.
You can get the advanced propagator by going both above and retarded by going both below, or vice versa. I forget which is which, but different choices of how to go around these give you different propagators.
So the Feynman propagator is a mixture of retarded and advanced Green's function.
No, I think
It's
it's the both is when you go both.
I guess maybe a more directed question is, why did we pick this one?
Yeah, basically.
This was our result. We know that this follows from our quantization of this three-scalar field. We can compute this. We know how to compute this. This is the result. I could work with this form of it and not write it as a contour integral. That will be more complicated. I tried to write down a contour, choose a choice of contour to agree with the result, which I knew already. This follows. All you need to do to get this result is combine the two possible time orderings of this result. This follows directly from the commutation relations for the ladder operators, which follows from the commutation relations for the field and its conjugate momentum.
But does that necessarily imply that we have to choose the semicircle contour in the lower half plane for minus EK and in the upper half plane for plus EK? Because I think that's the question. Like, it could be both in the upper, both semicircles could be in the upper half plane, or both could be in the lower half plane, or like why?
This is if I chose a different contour, if I chose to go above on both, purple contour. Well, if x naught is greater than y naught, then the integral along the purple contour would be equal to the sum of the contributions from these two poles. So I would get an extra term over here, and I'd have 0 over here. That would not agree with our calculation. I'd have an extra term multiplying this theta and 0 multiplying this theta.
But can the final result depend on the contour?
You can define other propagators. The Feynman propagator is the useful one for quantum field theory because this object is central to our calculation. We were trying to compute the matrix element or the scattering amplitude, and by a series of steps, we could relate that to sums of products of these propagators, not the advanced or retarded. So advanced and retarded have many uses in classical physics for quantum field theory. This is the most important propagator. One last statement is that this Green's function, this is a Green's function. The propagator is a Green's function. That means if I apply the Klein-Gordon operator to this object, which I'll give a new name to, I'll call it the Feynman propagator, delta F. This is just, if we look at this form, we get a integral d4 k 2 pi cubed, pi to the fourth, I over k squared minus m squared. And when the derivative acts on the exponential, I bring down a minus k squared, and then plus m squared. And I've got the exponential. And so this cancels out, just giving a minus I. When we take the Fourier transform of the identity, which is a delta, is equal to minus I times delta. And so this is a Green's function. I didn't have to use the contour I choose. So the retarded and advanced propagators are also Green's functions. So we'll use this repeatedly in our calculation.
So a general solution can be built up in terms of the Feynman propagator as some linear combinations of basically you integrate over the Green's functions to build up a general.
Yes. Yeah, we could do the same thing to build up solutions of the classical theory. That's what you do. And in the quantum theory, we're also going to be using these Green's functions as building blocks to construct the general correlation functions we're interested in. Okay.
Sorry, in the last line, the d4k integral, what's in the denominator? I just can't read it.
This is k squared minus m squared plus I epsilon.
Okay, thanks.
Where epsilon is a parameter we're taking to 0 at the end of our calculation.
You have written dou square plus m square to be in the Fourier space as minus k squared plus m squared.
Yes, this is the Klein-Gordon operator in momentum space.
Should we have a different dummy variable k prime for writing the operator, and then we should have a double integral over k prime and k?
We could do that as well, but here I'm just thinking about this acting on x.
I think we're supposed to go to our group lunch.
Yeah, if you want to write this in terms of a Fourier transform, you can also. Thank you.